Good morning, students. Myself, K. Lakshmi, Assistant Professor in the Department of EEE, Chevrolet Engineering College, Lecturer 32, Unit 3, Magnetostatics and Amperes Law. Today topic is point form of Amperes Law. In the last classes, we discussed about the applications of Amperes Law, that is determination of magnetic field intensity for a infinite sheet. Now, this is the last topic in this unit 3, first part, that is magnetostatics and Amperes law. So, in this session, we discuss about the point form of Amperes law. That is simply Maxwell's third equation. So, we have to here prove Maxwell's third equation by using Amperes law. That is del cross H is equal to J. That is the theorem here we have to prove in this session. Okay. Now, actually, in electrostatics, with the help of Gauss law, we have to develop a concept of divergence. That is del dot B, del dot D is equal to 0, like that. In the similar manner, in this magnetostatic chapter, with the help of Ampere's circuit law to the differential surface element, here a concept that is curl is developed. So that's why in the last two Maxwell equations, that is del dot D is equal to rho and del dot B is equal to 0, like that. So del means divergent. So del dot means divergent. Here, with the help of Ampere's circuit law, we have to develop Maxwell's third equation, that is del cross H. The cross means it is a curl. As we already discussed in a vector, what is the curl, what is divergent, like that. Now, let us consider a differential surface element having sides delta x and delta y plane. So this is the differential surface having width delta y and height delta x along x and y plane. So we have to find the magnetic field intensity at the center of the closed path. That resultant of magnetic field intensity gives the del cross H value, which is a Maxwell's third equation. Now, the total magnetic field intensity at the point P, when you observe this figure, this is the point P. So we have to calculate the magnetic field intensity at this point due to current passed through this closed path. Why? Because as we already discussed that the magnetic field is developed due to passage of current through any conductor. So this is the closed path. So the current is passed through this closed path. Due to passage of current, the surrounding space, magnetic field is developed. That's why at the point P, which is at the center of the closed path, we have to calculate the magnetic field intensity. So the magnetic field intensity at the point P is expressed as Hx0 Ax bar plus Hy0 Ay bar plus Hz0 Az bar. And here, why? Because we have to write the H bar value in terms of Ax, Ay, Az unit vector. Because of that, it is developed due to impact of all the three coordinate axes. But what about Ax bar, Ay bar value and Az bar value? That will be discussed in the whenever we do the this class. So finally, first the expression for the H bar value is Hx naught Ax bar plus Hy naught Ay bar plus Hz naught Az bar. Whether the magnetic field intensity having value along X or Y or Z, that will be discussed throughout the theorem. Okay. And similarly, the expression for the current density is J is equal to Jx Ax bar plus Jy Ay bar plus Jz Az bar. To apply Amperes circuit law to this closed path, let us evaluate the closed line integral of h bar. Why? Because already we discussed the statement of Amperes circuit law. That is the line integral of h bar is equal to the total current passed through it. So the line integral of h bar value in this closed path A, B, C, D, according to as the direction of current along z direction, automatically h bar having no components along this direction. That means it has only components along x and y directions only. Why? Because the current passed through the z direction. So first we calculate the h bar value along the path A and B. So here, this is the A and B. Now we have to calculate the magnetic field intensity at the point P due to this path, that is current travel from A to B. Similarly, magnetic field intensity developed when the current passed from B to C path. In the similar manner, C to D and D to D. Why? Because as the current direction is changes, the coordinate axis, whether it is positive or negative, also changes. So we have to take all these considered to calculate the h bar value. Okay. So first we calculate the h bar value at P due to current travel from A to B path. So this is the expression. What is the meaning of h bar dot dl? It is Ampere's law. So we have to calculate the h bar dot dl value. Here dl is the length from A to B. So in the suffix, the indication of A to B means current travel from A to B point. Now this value is equivalent to Hy naught plus delta x by 2 dou Hy by dou x. Why? Because this is the sum of the impact of h bar due to x and y. Here Hy naught is the magnetic field intensity at point P due to A and B. Now the rate of change of Hy, that is expressed as dou Hy by dou x. This is the value along x direction. So here the distance in x direction A to B from point B is delta x by 2. That will be clearly explained by the figure here. So this is delta x. So the half of the delta x by 2 is here. This length is equivalent to delta x by 2. So whenever we have to calculate the magnetic field intensity at the point P, when current is passed from A to B, then this value is equivalent to hy naught, and also impact of x direction also. That x direction impact is indicated by the expression delta x by 2 dou hy by dou x into delta y. This is the expression for the h bar, and delta y is the expression for the dl. Why? Because the distance from A to B is delta y. This is a totally expression for the h bar. H bar at P due to current passed from A to B direction. And the delta y represents the value of dl. The delta y is the distance between A to B. The same manner, we have to calculate the here for the path B to C. So this is a negative x direction. When you observe this figure, this is positive x, and B to C is along negative x direction. This is positive x, this is a negative direction. So that's why the unit vector we have to take is minus ax direction. Then automatically the magnetic field intensity at the point P for the path B to C is expressed as minus hx ax bar. Minus hx ax bar. And as usually, dl is the length between B to C. Whenever we have to put a bar on the top of the any letter, compulsory we have to take a unit vector in that direction. So is it clear? H bar is a magnetic field intensity. Along negative x direction, it is equal to minus hx ax bar. Similarly, dl bar is a vector. So actually dl value is equal to delta x. Whenever we put a bar on the top of the dl, we have to write unit vector also. So that's why dl bar is equal to delta x into ax bar. Okay, according to Amperes law, the line integral of magnetic field intensity, that means h bar dot dl bar. Here the h bar value is equivalent to minus hx ax bar dot dl bar value is delta x into ax bar. Simply multiply both these values. By multiplying both these values, so hx hx dot delta x so here a dot ax value is equivalent to 1. So simply we have the value of minus h into delta x. So that is the value here. Okay. Now, in the similar, whatever we have to take the magnetic field intensity at the point due to A to B, here also we have to take the value of hx. That means for the path B to C is expressed as hx is equal to hx 0 plus del y naught dou hx by dou y. So when you observe the This is the along A to B path. This is the expression along B to C path. The only difference is it is a negative x direction and the magnetic field intensity expressed as a Hx component. Now, finally, H bar dot dl for the path B to C is expressed as minus. The minus means negative x direction. Hx naught plus del y by 2 dou Hx by dou y, and the dl value is del x. So, from equation 6 represents the magnetic field intensity at the point P due to current passed from B to C. And the same we have to follow for the path C to D also. So when you observe the figure, C to D is the negative y direction. C to D is, this is the positive y direction. This is the negative y direction. Okay. So you have to imagine this figure in a three-dimensional view. As we present this experiment, this figure in a two-dimensional view. So you have to imagine this figure in a three-dimensional view. Then the negative side, it will comes to the, this is the positive y direction. This is the negative direction. As you observe the direction, this is the direction from A to B. That is a positive y direction. When you observe this figure, the direction of the current move towards the negative side of the y direction. It is clearly observed that the direction of the current is moved towards the negative side of y direction. Here, the direction of the current indicates it moves towards the positive y direction. So that is the main point you have to remember, that why the expression for the H bar C to D, we have to write a minus. And as usual, this value is equivalent to H y naught minus delta x by 2 dou hy by dou x. Dou hy by dou x. Okay. Both x and y are in a negative direction. Here, the negative x direction. Okay. And now, in a similar manner, that is, we have to, whatever we have to calculate the magnetic field intensity for when current passed from C to D, the same way we have to calculate the magnetic field intensity when current passed from D to A. So it is expressed as, it is in a negative y direction. So H bar dot dl bar value D to A is expressed as Hx naught minus del y by 2 by dou Hx by dou y into delta x. So these are the total expressions for the magnetic field intensity at the point for a closed path. Already in the starting, we discussed about the H bar have no components along z direction. That means it has only components along x and y. Why? Because the current direction is along z direction. So by the addition of these all values here, that is H bar dot dl bar is equal to Hy naught del y plus, simply we multiply the del x. So that's why here Hy naught delta y plus delta x delta y by 2 dou hy by dou x minus Hx naught delta x minus delta x delta y by 2 dou hx by dou y minus hy naught delta y plus del x del y by 2 dou hy by dou x plus hx naught delta x minus del xy del y by 2 dou hx by dou y. So here, is there any cancellations? So when you observe that, here plus delta x delta y by 2 dou hy by dou x. Here also delta x del y by 2 dou hy by dou x. So here we have to, by adding 2, so here hy naught delta y positive minus hy naught delta y are cancelled. Similarly, hx naught delta x positive, negative minus hx naught delta x and hx naught delta x are cancelled. When you observe these two values, here the finally we got 2 delta x delta y dou hx by dou x. Again in the denominator there is a 2. So 2 are cancelled. In the similar manner, by adding these two terms, we have to got delta x delta y dou hx by dou y. That means by adding these two equations, we get delta x delta y dou h y by dou x, and by adding these two equations, it is equal to delta x delta y dou hx by dou y. So by commoning these two terms, delta xy and delta y, that is so integral h bar dot dl bar is equal to, by commoning of delta x and delta y value, dou hy by dou x minus dou hx by dou y is the resultant value. But according to Amperes circuit law, this line integral of h bar value is equivalent to current. So current I, we have also expressed in terms of current density as current density into area. So here the current is passed through along z direction. So that's why the suffix we have to write the z for the j. So z means current density along z direction, and area, length into breadth. The area of the closed path length is delta x and breadth is delta y. So in place of I, we have also write as j z delta x delta y. Now equating both these two, by equating these two according to Amperes circuit law, on both sides, so here integral h bar dot dl, when you observe this, by cross multiplying this value, actually here we have to equating that, for example, by equating jz dx, equivalent to Jz delta x delta y here. So by cross multiplying here, that means integral h bar dot dl bar by delta x into delta y value is equivalent to Jz. So by equating this equation, we got integral h bar dot dl value by delta x into delta y is equal to dou hy by dou x minus dou hx by dou y is equal to jx. Okay. Now, this is the magnetic field intensity for a closed path whenever the current passed through a z direction. So that will be equal to Zx. In the similar manner, we have to also calculate the magnetic field intensity at the point P due to closed path when current travels in a y direction and x direction. So these are the expressions. So here, this is the expression for the magnetic field intensity where a current passes through along z direction. So that will be equal to Jz. In the similar manner, when current moves along x direction, this is the expression for the magnetic field intensity. And similarly, when current passes through y direction, that means the closed path, we have to take the remaining two coordinate axes. That means as current passes through x direction, the closed path is along y and z direction. So automatically the expression for the magnetic field intensity when current passes through x direction is, this is the expression. So this is the expression. In a similar manner, as current passes through y direction and the plane is along z and x direction, automatically this is the expression for the magnetic field intensity at the point P. This is the point. Okay. Now, in general, the expression for the magnetic field intensity is limited delta S n tends to 0. Integral h bar dot dl bar by delta Sn is equal to Jn. So, next, Jn is the current density normal to the surface delta S. Now J is expressed as a Jx Ax bar plus Jy Ay bar plus Jz Az bar. Now we have to substitute the Jx value here. So what is the Jx value? So this is the Jx value. Dou Hz by dou y minus dou Hy by dou z. Now substitute here. Similarly, Jy value and Jz value. So this is the current density expression changed by taking Amperes circuit law. So this is called curl H. As we already in the discussed the properties of vectors, the expression for any curl of a vector is, this is the expression. Dou hz by dou y minus dou hy by dou z ax bar plus dou hx by dou y dou z minus dou hz by dou x ay bar plus dou hy by dou x minus dou hx by dou y az bar. So this is the expression for the curl of a h vector. So curl means del cross. So simply del cross h is equal to, we got j. So this equation is called point form of Ampere's circuit law, or this is the Maxwell's third equation also. So this is the one of the Maxwell equation, or it is also called point form of Ampere's circuit law, or it is also called as differential form of Ampere's circuit law also. There is a lot of difference between Ampere's law and point form of Ampere's circuit law. Ampere's law is integral h bar dot dl is equal to I. And point form of Ampere's circuit law is del cross h is equal to 0. There is a lot of difference between Ampere's law and Ampere's circuit law. What is Ampere's law? Ampere's law is, so Ampere's law is h bar integral h bar dot dl bar is equal to I. Point form of Ampere's circuit law is curl h. That means del cross h is equal to j. Del cross h is equal to j. So this is called integral form of Ampere's law. This is called differential form of Ampere's law, or it is also known as point form of Ampere's law also. So today class is completed.